We are solving question number 35 of GATE 2016 chemical engineering paper. The question is water with a density of 1000 kg per meter cube is pumped at the rate of 36 meter cube per hour from tank 2 meter below the pump to an overhead pressure vessel 10 meter above the pump. The pressure values at the point of suction from the bottom of tank, at the discharge point, and at the discharge point to the overhead vessel are 120 kilopascal and 240 kilopascal respectively. All pipes in the system have the same diameter. Take acceleration due to gravity, g is equal to 10 meter per second square. Neglecting frictional losses, what is the power in kilowatt required to deliver the fluid? So over here we have been given that tank is placed 2 meter below the pump. If this is the pump, so suction will be at the bottom of the pump, and this height is 2 meter. Then the discharge is at the tank at the overhead pressure vessel 10 meter above the pump. If this is the tank, then this height is 10 meter. Then the density we have been given as 1000 kg per meter cube, and the flow rate Q dot is 36 meter cube per hour, and the pressure values of the suction from the bottom of the tank, that is at this point. At 1 we have the pressure value of 120 kilopascal, and at discharge, that is at second point, we have the pressure of 240 kilopascal. So all the pipes have same diameter, and the value of g is 10 meter square, 10 meter per second square, and we have to find the power required to deliver the fluid. So we can write the energy balance across this system, and it will result in the Bernoulli equation of the form P2 minus P1 upon rho plus half of V2 square minus V1 square plus G H2 minus H1 plus summation of F plus shaft work is equal to 0. Now, in this question, we have been given all the pipes in the system have the same diameter. That is, the velocity of the fluid at 1 and 2 will remain the same. So we can cancel the second term. Now we will be having pressure head due to this height difference of 10 plus 2, that is 12 meter. We haven't been given any frictional losses, and have been specified that neglecting the frictional losses, so we can take this term also as 0. And then we have to find this work from which we can find the power required to deliver the fluid. So we can replace the values over here. So P2 we have been given as 240 and P1 as 120 kilopascal. So we will keep the units as kilopascal only. So it will become 240 minus 120 upon rho is 1000 plus G is 10 . 10 into H2 minus H1 is basically 10 plus 2 will be 12 plus shaft work is equal to 0. Now this was in kilopascal, so we can change it into pascal by multiplying it by 1000. So ultimately this will be, the pressure will be in pascal upon the density, so that will become, let's just write this as 240 minus 120 is 120 plus 120 is equal to, you can write it as work. So this will be equal to 240. It will be kg per meter cube and Pascal. So the units of this work will be joule per kg. So the work required to shift the water from by the pump will from the to the height of 12 meter from the suction point will be 240 joule per kg. Now the power required, we can write this as mass flow rate into work. So the mass flow rate we have to find it in kg per second. So since we have been given the flow rate in 36 meter cube per hour, we can change it in kg per second as density is 1000 kg per meter cube. So 36 meter cube will be equal to 36,000 kg. And over we can change it into second as 3600 second. And then the work we found out to be 240 joule per kg. So ultimately we will be having 2400 joule per second as the power. So this is equal to 2400 watt, and we have been asked to find the power in kilowatt. So it will, the power in kilowatt will be 2.4 kilowatt. So the final answer we can select as option B, that the power required to deliver the fluid will be 2.4 kilowatt.